Good morning to everyone on another sunshiny, cool day. Makes you think summer's coming until you walk out there without a coat, right? Questions about a plus b to the second or the third or the fourth or the fifth. We had a lot of fun yesterday. I did manage to get before 5 o'clock the links to the video tutorials set up, but they were obscurely located. You had to look for binomial to the second, or say I had binomial to the third, binomial to the fourth, binomial to the fifth, and then I have Pascal's triangle and a couple other links, but you'll have to go under B for binomial. I didn't know how else to put that in there. And I have two links in factoring. So factoring a difference of squares, factoring a trinomial perfect square. So there's about a half a dozen links I created yesterday afternoon in the video tutorial. I last night got the board presentations arranged, or at least reversed image and such, but I won't get those placed on the server until about probably noon, somewhere in there. And hopefully we'll get today's presentation up there quickly and be in business. Watch the door, please. Thank you. Now, questions about the homework. The first 30 problems I'm hoping were fairly straightforward. The 51st problem may have been a challenge. But are there any questions in the first 30? Okay, so we're okay there. And in the 51st, it was just tedious? Yes, Vandy. 28, and page number, please?
251.
251, number 28. Okay. This is a sum and a difference. Okay, Debbie, let's try that. And we are in section 4.4 with the questions. And let me write that problem on the board while Debbie still has it up on the screen. This is 9y minus 2/3, and curl, you said one thing and wrote another. Not good. Let me try writing what I said. I was thinking fraction and immediately went into a fraction. And this is number 28. And we said page 251, is that right? Okay, what I'm hoping that you see in a problem like this is a minus b times a plus b, or an x minus y times an x plus y kind of arrangement. You see a pattern, because this is a sum times a difference. So the pattern we're talking about is seeing a plus b and a minus b. And you know that that is going to be a squared minus b squared. So if you know this is the pattern, and is that working better? Okay, getting a few nods that I'm looking in particular to get. Then I recognize I need 9y quantity squared just by substitution. And then I'm going to have minus 2, I'm sorry, I don't want to think of it as a minus 2/3 squared, but minus the quantity 2/3 squared. So I'm taking the square of each of the two pieces. So that's going to give me an 81y squared. And then the 4/9. Now, seeing the pattern is more important than seeing each individual problem as something uniquely different. I want you to start seeing the general patterns and what I was encouraging so much yesterday, working backwards. If you see something like 81y squared and a 4/9, you recognize it as 9y quantity squared and a 2/3 squared, and now you're seeing the difference of two perfect squares, which then can be written as a sum and difference in the product. Working this way, we referenced as being factoring. So thinking of it in reverse, every time you see a product, you're seeing a corresponding solution to a problem in factoring. And that is crucial in terms of where we're headed. Answer the question? Anybody else? Okay, at this point, then would you be kind enough to pass the papers over? And we will take care of that. And I thought we might just try a little review here from yesterday. I didn't assume there would be very many questions with the 30 problems. In your notes, let's see what you can do from memory without referring to what we did yesterday for a particular expansion. Okay, so what I would like you to do is just for the heck of it, a plus b to the fourth. Set it up and see if you can get it just by piecing it together with Pascal's triangle and knowing what happens to the exponents. See what you can do. And if you get this, then I'm going to be a real happy camper. Okay, Debbie, what we'll probably do is we'll just run a shot of the whole class, and I'll just meander around and enjoy some coffee and watch what people are doing. I enjoy, they work. This is good. Okay. We're taking a plus b to the fourth. See what you can put together here. And what you're trying to do is pick this up from pattern rather than grinding through the product of two trinomials, which could be done. Two trinomials will do it, and if that's the only way you feel you want to attack it, that's acceptable, but it's just, I'd like, if possible, that you do it in some other form. I want to just raise it up enough so I can see. Okay. Jeff. And somewhere your test proper itself is fallen out. I'll have to look for that. Okay, let's come back to the board. Now I agree, one way of doing this is to break it into this. And this is what's being suggested in your text. And this is an appropriate level to do the problem. But it is also painful. So in the sense that this is a squared plus 2ab plus b squared, and then you're going to multiply that times itself. And that will work. It's just, as I say, very tedious. So instead, we're hunting for shortcut. If you take a plus b to the fourth, you know it starts with a to the fourth, and it ends with b to the fourth. So somewhere down here, we're going to have a b to the fourth. Now, once you get that much, you know how the exponents behave. As the exponent in the a goes down, the exponent in the b comes up. So you know whatever we need a little bit of space for the coefficient, but you know that's going to go a to the third, b to the first. The next one has to drop down, and I think I may not have given enough space here. I know I have not given enough space, so let me add some space to what I need. I'll just clean that up so it'll at least photograph better. So I have a to the second, b to the second, then the next one's going to be a to the first, which we oftentimes just write as a, but then b to the third, and then the last one is just b to the fourth. Now one of the nice things is you're going to have a 1a to the fourth and a 1b to the fourth, so you don't have to worry about that. So the only question involves three spaces I have here. And that's where we try to pick that up from Pascal's triangle. So you argue 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. And if I want something to the fourth power, I go to my second entry as a 4. If I had a third power, then the 3, the second power, the 2. So I always look at the second number in on the row. So that means these are the coefficients. 1, 4, 6, 4, 1. Here's my 1, here's my 4, here's my 6, here's my 4, and here's my 1, and I'm done. And that's painless.
If it was cubed, it would be 1, 3, 3, 1?
You got it. Exactly. And that's what's so nice about Pascal's triangle. Now, so that you understand what would be happening here, when I say I have a to the second, b to the second, I'm asking how many different ways could I write a times b times b. So let's just focus on this for a moment. A, B, B. That's a squared, b squared. Well, Debbie, you'll be with me in a moment. I'll wait. There we go. And then I have what? A, B, A, B. That's still a squared, b squared. Or I could have A, B, B, A. Abba, dabba, dabba. Now, I could also have what? Instead of starting with the A, I could say B, B, A, A. Or B, A, B, A. Or B, A, B. All of those will give me a squared, b squared. How many of those arrangements are there? 6. That's where the 6 came from. We had, okay, we'll have to, not sure, okay. We have 6 right there. The 6 that's referenced there is how many different ways can you get a squared, b squared out of a product. That's all it means. And if you want to think in terms of what we're talking about, this is called a combination. So we use the letter C for combination. And I have 4 things, and I'm taking them 2 at a time. Hence, C42. And that would be the formal notation, sometimes written this way. So Pascal's triangle is giving you the answers to problems in combinatorials. So if I look at 4 points, form of a square, roughly, how many lines can I draw through those 4 points? 1, 2, 3, 4, 5, 6. And now it is a problem in graph theory. Finally, on a practical level, I was mentioning to Perry in an earlier discussion, in statistics, we have 220 countries in the world, roughly speaking. It's about 222 or 223 right now. And it's always changing. For example, in today's paper, Yugoslavia no longer is a word for a country. It's now Serbia, Bosnia? No. That's right. Serbia, Herzegovina, or Serbia, Bosnia. I'm trying to remember which way they did it. It was in the Chronicle this morning. And they are going to allow, it must be Herzegovina, because they're going to allow for it to become 2 separate states eventually. But it's, the number is in flux, whether a country partitions, becomes independent, but roughly 220. If I take 220 countries of the world and I decide to take a sample of 30 of them to find out information about the world, then C 22030 is the way I can do that. That's how many possible samples I could get. Now, you also need to understand that these numbers get large quickly. Pascal's triangle doesn't look too impressive in the first few rows. Let me just run that number through for you just to get a sense of how huge something like that could be. If you think of just getting 30 countries at random, you put the 220 names in a bucket and you pick a name out, put it back in the bucket, shake it up, pick another one until you get 30 different ones. Each one has the same chance of being selected. Now the question, how many ways could you do that? Think of your wildest imagination of how many ways maybe that could be done. You got a number in your head, I hope, or at least some magnitude to it. So with that, what I will do is take a calculator out, that we need to do this calculation. This happens to be the one that we use in stat. It's one of the few classes that I will tolerate having a calculator used. Okay, let's see. Okay, Debbie, let's cut to there. This is just the keyboard on this particular calculator, but down here at the bottom row where the 0 is, and I'm going to zoom down on that a little bit, see if I can do that. Okay, and then focus. See the C and R? That's the argument that we want. C, 220 taken 30 at a time. So as we come off there, what I'm going to do, and you don't need to see the particular data entry here, but I'm going to put my 220 into the calculator appropriately, take the 30, and then I'm going to ask it to give me the number that's calculated for the problem I have on the board. Let's see, I need something that's still reading better than that. Oh, why? I've got chalk dust on it, and it's picking up all the chalk dust. Debbie, that seems to be about the best I can do. There, I'll just shade it. Do you see the 8.89 roughly? Do you see that 36 on the far right? That's an exponent. So roughly speaking, let's just take 8.9. So we are saying, as we come off there now, 8.9 times 10 to the 36th power. I don't know if you have any sense of the magnitude of that number. Okay. You're going to move the decimal point 36 places to the right, so that means there's 35 zeros after the 89. Now that, by the way, is known as scientific notation, and that's one of our topics. So we're doing some algebra there. So let's just see what we get. 89 with 35 zeros. 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 34, 35. A little more impressive that way? Okay. Let's see what we can do to name some things here. Okay, those 1,000, million, billion, trillion, quadrillion, quintillion, sextillion, septillion, octillion, nonillion, decillion, so 8,900 decillion. Large number. Okay, now we do that in Math 10. We talk about how we name numbers. So my point being, would you want to go down to Pascal's triangle that far?
No.
Okay, I think the point's well taken. For lunch, by lunchtime. Now, where do you use the content of Pascal's triangle besides what we're doing here? I hope you understand that if we looked at problems in statistics, obviously it's there. It is in probability theory. It is in graph theory. You find certainly applications in algebra. And what I would like to bring to your attention, remember our discussion about Fibonacci numbers? You remember 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. We talked about Fibonacci numbers. Okay. I don't know how well I'm going to be able to show this with what we have. Well, let's see. I'm going to try diagonals, and I don't have this spaced very well to do this. There's one. There's the next one. Here's your next one. Oh boy. Now there's a 1 down here that goes with the next row. Okay, that we'd be picking up. It's actually with the 5. It's about out here, I think, so it picks that one up. Now, what is the total in that first diagonal? 1. Next diagonal. 1. Next diagonal. 2. Next diagonal.
3.
Next diagonal.
5.
And those are the Fibonacci numbers, and they just come out of Pascal's triangle. Okay. We'll see what's happening. Good morning, Jim Crow. Okay, it's not up on simulcast. Okay, we will have Debbie check that out. She's going to make a call, and we'll see what happened. I know the server was down at 7:30 to, I think it was either 7 to 7:30 or 7:30 to 8 this morning. But we're going to see, she's on another line, so if you'll hold in just a minute, Luis, we'll see what she finds out. So just hold on the line for a moment. Okay, Debbie, what did you find out?
He's got to check it. He's got to make some phone calls because we haven't switched here, so now we have to call people who do the server.
Okay, it's been switched here, and when they did the server this morning, it could be something as simplistic as somebody did not throw the switch there. So either it's going to be resolved shortly for you, or you'll want to go to the library and watch the VHS tape later. Hang in there and hope that it works. Thank you for the call. Add the rows. First row is 1. Next row, 2. Next row, 4. Next row, 8. Next row, 16. What is 1, 2, 4, 8, 16, 32? What do we know it as? Okay, again, 1, 2, 4, 8, 16, 32. Not squaring. Sort of a doubling idea. Okay, where am I going to find space? Debbie, we're going to migrate now. I'll just walk over there and we'll go to, that's good. Leave that up there. That's nice. Now what we're doing is adding the elements in a row. And I'm getting 1, 2, 4, 8, 16, 32. Pattern time.
64.
64, okay, good. Okay, got the pattern. Now how do I get it?
Double it.
You doubled the last time.
I'm doubling, right? Okay, mathematical symbol for doubling. Now squaring is different than doubling.
Well, 2.
2 to the blank. Okay, 2 to the blank.
Over the end.
Okay, let n be 0. What do we get? 2 to the 0. 2 to the first. 2 to the second. 2 to the third. 2 to the fourth.
Right.
2 to the fifth.
The 6.
Okay.
Now, squares of 2, powers of 2. So we're getting powers of 2. So the sums in the rows are powers of 2. What did we find out?
We're getting it in the office, so it is streaming on campus. Now they're going to check off campus.
Okay, so stream control. Where do you use this? This becomes our method of deciding in a, you're familiar with bar graphs? You've seen bar graphs in business applications. They're called histograms, and we use this to decide how many bars we're going to have. So the point being, so much comes out of this triangle, and so much of mathematics. This is the stat course involvement. The C20, 220, 30, what we did there naming that, that's math 10. The work in geometry with how many lines can you draw through 4 points, that's a geometry problem. Obviously we do it in binomial expansion. And just, oh, by the way, let me come back to one more I can't pass up. A quiz. 20 questions. The infamous, let me get another piece of chalk, the infamous multiple choice quiz. 5 parts. Guessing through your teeth. Does happen occasionally, particularly if you're doing job applications. One comes to my mind is I had a former student whose background was in chemistry, and she saw a job announcement for a county position, and she decided to go for the interview, and they had a little test they wanted her to take. It was on gas chromatography. Basically, you burn a substance, see the color of the flame, and on the basis of the color of the flame, you identify the substance. She'd never had such a course and was given the test, multiple choice. You are guessing through your teeth. Second example is my youngest son attending the Monterey School for Language at Monterey, had to take a test to determine his proficiency in language study, in which they created an artificial language you knew nothing about, told you some rules, and then gave you test questions. So you have a nonsense syllable, and if you put these nonsense syllables together, what might it mean? So again, if I took that test with my language ability, it would be totally guesswork. Okay, so what is your chance of guessing a correct answer? 1/5, 1 out of 5. And of course, not guessing a correct answer is 4/5. So you got an 80% chance on each question of screwing up. And so you can ask, what is the chance that out of these 20 questions you would get 15 right? So what is your chance, guessing through your teeth, of 15 correct answers? Now, technically, you'd like 15 or more, 70% or above, but let's say 15 or more correct answers. How do you find this? Here's what you do. You take a plus b to the 20th power. The binomial expansion that we've just been doing is precisely what you do there. And you run it down until you get to the 20th row, and then you want 15 at a time. So you have to count over 16 points or positions in the row to get the answer. That becomes your coefficient, and so you would, I'll just show you what you would get for that. You know how to find this now with Pascal's triangle, and you take p to the 15th, q to the 5th. That would be the answer to your question, and that's where we use what we've been doing in this class the last 2 days. Stat. And a very interesting little problem. Guessing and getting answers right. So I'll leave that there, and I'll just walk back up front. So I thought that was sort of neat to share some of the things that we can do. One of them that becomes very practical is in lie detectors, because the courts have ruled lie detectors as not being accurate enough, and the argument is that you can take 20 people, have them take the lie detector test, and all of them be telling the truth, and it will dictate a certain number are lying. And so you can find the chance out of 20 people taking a lie detector test, what's the probability of 15 of them coming out as lying? Same kind of problem. All very fascinating. Out of that comes an idea that, just in passing, mathematics isn't isolated. You start talking about one topic, and it just starts going all over the place. And it's that, in a sense, that justifies why you get the algebraic background. Because with the knowledge of algebra, you can talk about other problems. You cannot talk about that problem in stat, either of those two examples, without the algebra background. The binomial expansion that we're talking about yesterday and today, one of the most critical things for that course. In terms of going on in mathematics, you need to know how to do it. And there's a phrase that we talk about, working smart, doing something so it doesn't chew you up. You find a way of doing it without getting so tedious. Eating smart, we have all sorts of phrases we talk about now. But the idea is there's a hard way of doing something, and then there's a smart way of doing it, and the smart way saves you time, but doing it the hard way will chew you up. Pascal's triangle is the smart way of doing expansions, and it pays to play with it a little bit and get comfortable. And you'll see it again, assuming that you're taking this course, so that you can go on and take another algebra course, so that you can meet either a requirement for an upper, well, most of you, if you're thinking in terms of transfer, are going to be facing a situation where you're going to talk about a 100 level course, so you don't have to take a test when you get to the 4-year school in mathematics. It's called the ELM test, Elementary Level Mathematics, which is a test in algebra and geometry. And you avoid that by taking a 100 level course. So that means a 70 and a 90 and then one more course. And there are a variety of operands in the 100 level, stats one of them, 101's another, 121's another one, and they all have different orientations. 138, a business, social science, behavioral science, biological science, calculus course after one more semester of algebra. So we're opening doors. That's the whole idea. Okay, we go into the next section. I wanted about a half hour to do that, and I've got it. So let's look at page 254. Where does the number 254 come in? Anybody? Off the top of your head? 2.54? Sorry about that, Debbie. Right in your ear, right? 2.54. How many centimeters in an inch? 2.54. Okay. I'm impressed, Michelle. Now, here's a to the 0 equals 1. This is on page 254, the centimeter page. We have a to the 0 equals 1, assuming a is not what? 0 itself. So let's come off there for a moment, because the next part I'm going to go to is one that, okay, how do I want to say this? One way of looking at algebra is a little bit like you're looking at rules of a game, how you interpret certain things. If, as a kid, for various reasons, kids get nicknames. Okay? So, you have a formal name, and then you have a nickname. I have an uncle whose nickname's Buddy. I think it came out of the idea that when they were kids, they couldn't say his name, which was Calvin. So it became Buddy. With one of my grandsons, I'm Paka. He couldn't say Papa, he could say Paka, and so now to that particular group of grandchildren, it's called Gavinese. Gavin's his name, and so he developed that for my name, and so my son says, well, according to Gavinese, which now my granddaughter has picked up, it's all the kids, I'm Paka. I would have never thought of all the things that a grandfather would be called. Paka would not be one of them. Now, if somebody says, well, why are you Paka? What reasonable answer can you give? That's just what my grandson could say. So that's what I'm called. Now, that doesn't make you understand anything more particularly of what Paka means. It's just that is the name given to me by a certain grandchild. So I'm Paka. Same spirit. I'm going to ask you to see what we do next in that same spirit. Okay. Let's see if I can get this in a little easier to read statement. It's always a battle with this text and the way it seems to allow me to zoom in on something and keep clarity. Let's try that. Okay, it's what do you mean by a negative exponent? A to the minus n. I'm going to have to, again, travel. A to the minus n. Now, if you just saw an a to the minus n, I would suspect you'd have absolutely no sense of what it means. In the same way, I could say I have 10 to the minus 3. There's an example. 10 to the minus 3 versus a to the minus n. You have no more sense of that than if somebody says, there's Paka, and you say, who in the heck's that? But we're going to agree. Now, notice this statement here. We are going to agree what it means. When you see this, you understand that this is understood. Now, that doesn't give you understanding per se in the sense of, I know why it's done. It's just, that's the agreement we make. 10 to the minus 3, therefore, means we agree as 1 over 10 to the third. Now, there are some things that motivate it. But even without anything else being said, you would just have to agree That is the way we interpret some mathematical notation. You may not feel comfortable about it. Don't get your comfort level confused with understanding. Big difference. Now, why might we do something like that? Well, let's look at a problem I talked about earlier. Let's see, where do I want to do this? I guess I can do it here. Place value chart. We're familiar with the decimal point. The first digit to the left of the decimal point is the ones place, correct? But we know we could write that as 10 to the 0. Again, why? By agreement. There's some justification for it in the moment. The next place to your left is 10, which we could call 10 to the first. The next place value to your left is 10 to the second. And we know we go to hundreds, thousands, 10,000s, 100,000s, millions, and so on, and we get up to quadrillions and quintillions and so on. But if we go this way, I hope you remember the days when you learned about decimals. We said as you go to the right now, you divide by 10 each time. So you argue that the value here is a tenths place, ends in th. So you say 1 over 10 because you divided by 10. Then you divide by 10 again, and you get 1 over 100. And then you get 1 over 1,000. And I think you're all familiar with that. Well, if I look at the place values and now think in terms of what happens to the exponents on 10, 10 to the second, 10 to the first, 10 to the 0, they just step down 1 each time. So what's the next one under 0? Well, that would be 10 to the minus 1, and 10 to the minus 2, and 10 to the minus 3, if I was going to follow the pattern. But then 10 to the minus 3 would have to be what? 1 over 1,000, which is 1 over 10 to the third. So just to make this pattern work, we'll just argue what? 1 over 10 to the third means 10 to the minus 3. And now the pattern sort of works and makes life better. I'm going to give you another illustration to motivate this. If I write 5 times 5, and I have here 5 times 5 times 5 times 5, I have a fraction, which we would typically reduce, correct? So you would reduce this and say, well, the 5's up here are gone, and I have 1 over 5 times 5, which is 1 over 5 to the second. Are we okay there? What we're getting ready to do is subtract exponents. Now, we've already seen what happens when we multiply bases together. A reminder. If I had 5 to the second times 5 to the third, what was your shortcut? That was a bad choice. I don't want more 5s running around here. 5 to the second times 5 to the fourth.
Add the exponent.
You would add the exponents and say 2 plus 4, and you would argue you have 5 to the sixth. Agreed? Now the question. This is like 5 to the second over 5 to the fourth. Instead of multiplying, I'm doing what? Dividing. So the obvious question, do you have a similar process of addition when we do division? That is, we added when we multiplied. What do we do when we divide? And the answer is subtract. So you argue that this is 5 to the 2 minus 4, but that becomes what? 5 to the minus 2. If that rule is going to work, what do you have to agree? That 5 to the minus 2 is 1 over 5 squared, and so that becomes part of the justification so that everything works smoothly. The rules work. This is like making sure you have synchro gears in your transmission. Same idea. So we are going to define certain things so all the pieces go together nicely. This adds to your comfort level eventually. It's just at the moment uncomfortable if you have not worked with negative exponents. Now let's go back to another statement we made. We said a to the m times a to the n is equal to what? A to the m plus n, but what was our restriction at the time? M and n were, okay, we thought of them as positive integers, non-zero, but integers too. And of course it works for fractions, but we haven't made any sense out of an exponent that is a fraction. So far we've limited things. But then the question, what happens if you had 5 to the 4th times 5 to the minus 2? And the answer is going to be, add the exponent still, 5 to the 4 plus negative 2, which is 5 to the 2nd, and that would work. Because what is 5 to the minus 2? 1 over 5 squared. So I have 5 to the 4th over 5 squared. That is going to be 5 squared. These are all arguments hoping that you feel comfortable with our definition. But as a definition, going back to that phrase that comes out of Shakespeare, a rose by any other name would be as sweet. Whether you call it a rose or a bramble, still the same element, the same thing, same characteristics. You just give it a different name. Okay, we'll leave that up there for a moment. That's where we're headed. And I've covered a whole lot of mathematics in the process. You have to be careful with exponents in the sense that a problem like this one is a classic blunder problem. Okay, let's cut to it. 4 to the minus 1 minus 2 to the minus 1. Nothing but a bunch of minuses running around, right? 4 to the minus 1 minus 2 to the minus 1. And this is on page 255. So 255, if you will go to that page. So all we're trying to do here is get you comfortable with new notation. Let's come back to the problem. Now what is 4 to the minus 1? Interpret it. It's not negative 4. That's the first thing. It's 1 over 4 to the first, which is another way of writing 1/4. Okay, I'm going to leave that there. I need another wall of boards today. Should go to Walmart, right? Okay, we have 4 to the minus 1, and I have minus 2 to the minus 1. Now the thing you have to understand, there's a difference in where I'm putting the minus signs. If I put the minus sign in front of the 4, that's a very different animal. But putting it up here as an exponent, it means 1 over 4 to the first. Do you need the first? No, but it might help you remember what happened. Then minus 1 over 2 to the first. Okay, so that becomes 1/4 minus 2/4, so you have negative 1/4, which could be written as negative 4 to the minus 1. Okay, we're moving symbols around and having fun. Okay, well, some of us are having fun. As long as I'm having fun, that's my biggest concern. You find a similar problem down here trying to point out to you that this is the bottom of 255. This is a cautionary kind of note, and it just makes the comment here that a negative exponent does not indicate a negative number. 3 to the minus 2 is 1/9. That's positive. A negative 3 to the minus 2 is negative 1/9. You can't look at these two negatives and say somehow or the other they're canceling each other out. Position is very important. Minus 3 to the minus 2. What happens if you get sloppy and do this? That's even more sloppy than I wanted. You have no idea what is meant for sure. One possibility is negative 5, but maybe somebody left a dot out and they really wanted positive 6. Where you locate this minus 2 is very critical to how you interpret it. Exponents must be written carefully. Subscripts and superscripts. if I have, in the same way, negative a to the minus 2, okay, that's going to be negative 1 over a squared. Now what you can see with numbers, think of rewriting for yourself with letters to make sure that you have a comfort zone with these symbols. There's a cute cartoon that I had a student a number of years back who was very clever in cartooning and drew a cartoon of numbers and symbols chasing her at night in her dreams. And there'd be an X chasing after her and a square root of 2 and a pi symbol. And if you aren't comfortable with symbols, this has got to be overload. Yeah, more symbols. And of course, one of the justifications of having you take algebra background for like chemistry and physics and biology and statistics, those are all courses that are heavily into symbolic notation. And if you don't do well with letters of the alphabet being used in different ways, you see a periodic table, and you have to do that in chemistry, and if you can't let letters represent something, life could be a little bit awkward. Well, let's see. I have in the process, on page 257, addressed this new equation. So, Debbie? A to the m over a to the n will be a to the m minus n. So if you're dividing and the bases are the same, you subtract the exponents. And be careful, you may get a negative exponent for an answer. Okay? This next one is on the previous page, and it seems to me a little bit out of context, relatively speaking. This is the question of how do you play the game. Watch this one. A to the minus m over b to the minus n is the same as b to the n over a to the m. Well, it's sort of an inverse rule. It's reciprocal. And what it amounts to, if you have a negative exponent in either the numerator or denominator, you can relocate that term in the opposite position with a positive exponent. Now, let's come off there for a moment, Debbie, and let's see if I can get the old book to hold a position and bring this up a little bit. Okay, that looks pretty good. Let's go back to that. And what I want to do is, how could you establish that? Well, first, if I have a to the m, God, talk about position, a to the m over a to the n to the negative 1. Think of that one, to the negative 1. Then I could say, bring the exponent across, so that is a to the m to the negative 1 over a to the n. I am saying a to the m and writing a sub n. Not good. So that is the same as I have up here, but then that is a to the minus m over a to the minus n. But this says take the reciprocal, which is 1 over a to the m over a to the n, which means turn it upside down, which is what the argument is here, that that's a to the m n over a to the m. Now I used a's here. The only difference in the text, he's doing what? Using b's and a's together. Let's go back to the text. So you have an a to the m over b to the n kind of thing. So let me just change some letters here so it makes it a little bit easier to see what's being done in the book. What I'm trying to get at is it looks like a capricious statement. We'll just flip things over, but you could defend it. Because a minus 1 says take the reciprocal of something. So if I say that I have a number to the minus 1 power, like we did 4 to the minus 1 as we slide over, where I have this 4 to the minus 1, that says take the reciprocal, 1 over 4. 2 to the minus 1 says take the reciprocal. So if I had this expression, a to the m over b to the n to the minus 1, it would say take the reciprocal. And how do you do a reciprocal? turn upside down. I think that's what Michelle was noticing. You're turning something upside down. But if you're going to try to defend it, you can go through little operations like this and consider that a kind of argument. This either is convincing or confusing, depending on how comfortable you are with the notation. Okay. Most of what we're doing here is going to be juggling symbols, and it is at times a little bit overwhelming. But if we put all the things we've done together into one nice little table with examples, on page 258, this is now what you should know. And that isn't reading. Blue just doesn't work well here at all. And if I try to darken it, I lose it. Page 258, you have power rules, quotient rules, product rules, zero exponents, negative exponents. Coming off there because it's not reading well at all. Let me zoom in a little bit. Okay, in pieces. Now, let's try it, Debbie. Product rule. And you can see it's on the page, but just scrolling up, there are a whole bunch of rules you need to know. So what is your one obligation for tonight's homework?
Learn those.
Read the rules, know the rules, be able to use the rules. Read, know, and use. Reading them is not enough. Knowing them is not enough. Using them is the bottom line. Let's see what kinds of things you'll be asked to do in sort of a first reaction might be, I don't want to do it. Okay, here's a problem on page 259. 3x to the minus 2 over 4 to the minus 1, y to the third, all to the negative 3. Infamous statement, simplify them. And 259 at the top. So let's come off there for a moment, Debbie. That's not reading well at all. So we'll just try to get down to the point where it is big enough. This, try that. That's the problem we want to do. And the key phrase, simplify. Now, the key. What you learned with positive exponents works with any exponent. That's the key. You aren't having to learn something new. My problem is, where in the devil am I going to find room to do that? Well, we're just going to walk our way through this step by step on the document cam. Look at the first step. Note you needed a 1 with that 3. Now the 3 I'm talking about is right there. That was 3 to the first. Okay? So when you get this 3 to the minus 3, what happened? The exponent was multiplied across. And the the x to the 6th, what is minus 2 times minus 3? 6. Hence the x to the 6th. Then you can do what with the minus 3? Pull it right down here in the same game. Negative 3 times negative 1 is 3. Hence, 4 to the third. You have y to the 3, all to the negative 3. Negative 3 times 3, negative 9. Now, in a sense, you've played the game, but I think what's going to be intended here is get rid of the negative exponents. So now what do you get to do? If you had 3 to the minus 3 in top, it becomes what? 3 to the third in the bottom. The y to the minus 9 in the bottom becomes what? Y to the 9th in the top. So I rewrite here. Then, next step, as you watch the screen, 3 to the third is 27. 4 to the third is 64. So then you get to do what? Multiply that garbage together, and this is your final answer. Do you recognize 1,728, anyone?
No.
Keep thinking. 1,728. How many cubic inches in a cubic foot? 1,728 cubic inches in a cubic foot. 12 by 12 by 12. 12 gross would be 1,728. Look at the little warning down here. Since the steps can be done in different orders, there are many equally good ways to simplify a problem. There's no one way that you are obligated on these. The danger is getting lost in an abyss of symbols and not having a sense of where you're going. Well, let's see what kinds of problems we can enjoy. I looked and both went up at the same time.
Go ahead.
Okay, Michelle.
When you have the second part where you have 3 negative 3x to the 6th over 4 3 y to negative 9, you're just flipping the negatives. You can separate them and flip just the 3 and the 9.
Okay, let's come to the place where Michelle's asking. The key.
Yeah.
Now, see, that was what we just did in the sideboard, but the argument is if you see a 3 to the negative 3, if you put that 3 in the denominator, it'll go to a positive 3.
But you can separate the 3 from the x?
The 3 from the x.
You don't have to.
They're
take
together
this.
on the top line.
Well, there's an implied product. That's 3 to the minus 3 times x to the 6th.
Right.
They are factors. And in a sense, you would argue what? 3 to the minus 3 is 1 over 3 to the 3rd? That forces it into the denominator. Then in this denominator, you have y to the minus 9. But that's 1 over y to the 9th. But it's a denominator, so you take the reciprocal and multiply, and you get y to the 9th in the top. What is implied here is a very good understanding of fractions, from arithmetic, and taking reciprocals, and having done it in the last 30 days. That not being the case for most of us. You're going to find a discomfort level in this process. The real interesting problems that you'll have a fair chance at are on page 261 at the top, doing the kind of thing we taught. I'm just going to drop down now. There's number 69. It's Debbie off of, well, I'm having trouble getting the camera angle so it'll read well. There we go. There's 69, scrolling, not strolling, but scrolling. Another one that's fun. 71 is fun. Fun in the sun. Okay. Now, as we come off there, at the bottom of 260, they are a little less intimidating. Read very carefully the directions, and oftentimes it'll say, rewrite with only positive exponents, and you can see that statement right up here. So there are very strict rules you're following here as you go through. Going up further, this is in 260 near the top of the page. Again, we want these with positive exponents. So if I think of number 41 with what Michelle just asked, can you in your head give me the answer? 5 to the 2nd over 4 to the 3rd. Done. So minimally, write the problem. And when it's possible to do that quickly in your head, then the next step, at least 2 steps, the problem and an answer. For your own health, try to have a few intermediate steps. Debbie, we're running out of time. The homework will be 1 through 72 all. That too many? Probably is. I'll rephrase that. 1 through 71 odd minimally. And I'll take those. But I would try to do 70 and 72 and 261 just for the practice. But 1 through 71 odd. Debbie, as we close.
Santana, put your lights on.
Better not.
No? Okay.
That could be edited.
Okay.
Okay, let's try Maria, maybe?
Okay.
Let's go with that one. Have a great day.